Good evening, everybody. Welcome to the RASC Toronto Centre. It's our speakers night. Before I go any further, I just want to make sure that if there is anybody in the room who wants to be at first light, that's next door. And if you're expecting to be part of the great conversations, you need to be down at least one level, so not in here. So is everybody here for the speakers night of the RASC? First light. Okay. Okay. Next door. First Light is one of our programs associated with an introduction to astronomy. First Light. I've got nobody for you, Rachel. I'm sorry. All right. Everybody else is in the right place? Excellent. Okay. So, once again, thank you very much for joining us tonight. My name is Paul Delaney. I'm the second Vice President of the Toronto Centre. I'm a little taller than Ralph. Ralph's not here. And so he sends his regrets and hopes that we'll have a terrific evening. I thought about sitting down, but no, not good. Okay, so anybody here for the first time tonight? Welcome. So tonight is one of two types of event on Wednesday evenings that the Toronto Centre engages in. It's the speakers night, where somebody, in this case Jake, will be talking to us about some aspect of modern astronomy and astrophysics at the right level. And then in between our once a month speakers nights, we have what we call our recreational astronomy nights. So the next one will be on April 25th, and that's where a number of members talk about differing aspects of our hobby, of our craft, and so you'll find out sort of the behind the scenes of what you may or may not want to get engaged in yourselves. So those are the two types of meetings that we have. The only other comment was, well, actually, I guess we've done everything because we've found all of your folks. So, okay. So at this point in time, it's my pleasure to introduce our speaker for the evening. It's part of a York doubleheader. By now, you should be quite used to me dragging people kicking and screaming from York into this room. But it is Jake Kloos. He's one of our PhD students. Should be done about a year from now if all goes well. He's a member of John Moore's planetary team. Dr. John has spoken here on a number of occasions. Jake heralds from the sunny state of Arizona. You can ask him why on earth he came north, but that's afterwards. He completed his bachelor's degree there in 2013, came up, completed his master's degree with us here in 2016, and as you can see by the topic in front of us, he is one of those planetary scientists and meanders around the solar system, specializing in looking for water, ice and water. So without any further ado, it's my great pleasure, Jake Kloos from York, Icy Worlds of the Solar System.
Well, thank you all for coming. I'm very excited to be here and very honored to be invited to speak. So today I'll be talking about the presence of water in our solar system as it's been revealed through exploration over the last few decades. And there's been a lot of exciting findings with respect to water, and certainly ones that have really surprised us. So for the next hour or so, I'm going to take you on a tour through the solar system to kind of discuss what these icy worlds and the watery worlds that we find within it indeed are. So before I start that, I want to first talk about the significance of water, so why we care about its presence at all. Well, with respect to exploration, the answer to that question really has to do with our understanding of life and habitability. Our beautiful planet here is abundant with water. More than 70% of its surface is covered with it. We find it everywhere we look. We find it in oceans and rivers and lakes. We find it underground. We find it in the atmosphere in the form of clouds. It even sometimes falls from the sky, as it did today. And crucially, everywhere we find water, we find life. And so our understanding of life as we know it here on Earth really has to do strongly with the existence of liquid water. Now, that may not be the case for other worlds. There's a lot that we don't understand about life and how it began. But for the only test case that we have, water seems to be pretty important. And so it's a good starting point as we seek to answer this question of, are we alone in the universe? So the second reason water is significant is because it's a resource. And it's sort of tied to this first point. But as we start to think about human exploration to places like Mars, water is going to be very important in order to sustain ourselves. And so we can either bring it with us, which is fairly costly, or we can make use of the resources that are available on the places that we're exploring. So as a precursor, I wanted to show this plot. I think the astronomers in the room might be familiar with this, but this is showing the abundance of elements in the universe. So on the x-axis, we have the atomic number, which corresponds to the number of protons in the nucleus. So we're moving towards heavier and heavier elements as we move right on the x-axis. And on the y-axis is the abundance. So this is the amount of those atoms that are present in the universe. So I only want to show kind of a relative abundance here. But there are two things I wanted to point out. One is that hydrogen is the most abundant element in the universe, and that makes sense. It's the simplest element. That's one proton, one electron. But the second and less obvious point is that oxygen is actually the third most abundant element in the universe, after helium. And oxygen is a common byproduct in fusion from stars, and so it's ubiquitous in the molecular clouds from which stars and planets form from. So what this plot is telling us is that water, because the constituents of water, hydrogen and oxygen, are so abundant in the universe that we should expect to find water in the solar system. So before we dive into the tour, I briefly wanted to introduce this concept of the habitable zone. I think many people will be familiar with it. So this is the idea that there's this region around the star where the temperature environment is just right for the existence of liquid water on the surface of a planet. So it's not too hot where all the water would be evaporated. It's not too cold where all the water would be frozen. It's just right for water to exist in a liquid state. And kind of implicit in this concept is that in the outer regions of the solar system, water can't exist as a liquid. And this is something that I was taught growing up, but the last few decades of exploration of the outer solar system have really kind of shattered this notion. And so this idea of a habitable zone should really be kind of put in quotations. Okay, so the first stop on our tour is the moon. I'm going to spend a little bit of time talking about this because this is an area of research that I'm personally involved in. But many people are surprised to hear that water ice can exist on the moon. And that should be surprising because the moon has an extreme temperature environment. So at any given time, half of the surface of the moon is being illuminated by the sun. And those regions that are in direct sunlight experience really high temperatures. So the temperature can reach up to 120 degrees Celsius. And so if you were to place an ice cube at some random point on the surface of the moon and expose it to direct sunlight, the ice would immediately begin to sublimate. It goes from a solid directly to a gas. Sunlight can sometimes destroy the water and break it apart into hydrogen and oxygen, and the hydrogen will escape because the moon doesn't have a very high surface gravity. So for most of the moons, most of the regions on the moon, water is not stable. But there are some, and I'll get to those in just a minute. But first, how does the moon come to have ice? We have to answer this question of how is water delivered to the moon? Because when it formed, it likely didn't have a lot, if any. And so we have to answer this question of where did water come from? Well, most of the water most likely came from impacts with the body from comets and asteroids. Both of these bodies are fairly rich in water ice. Comets especially so. Here's an example of Comet 67P, which the Rosetta spacecraft explored, and an artist's conception of the asteroid Bennu, which OSIRIS-REx will be exploring soon. And so when these bodies collide with the moon, they deliver their volatiles, their water. And we know that these bodies have frequently collided with the moon because we can see the impacts that they have left behind. So a third explanation as to why water comes to exist on the moon is a little bit more difficult to understand, but it's the idea that solar wind is interacting with the regolith. So the moon is constantly subjected to the solar wind, which is radiation, and protons, which are hydrogen nuclei, and these hydrogen nuclei can bond with spare oxygen atoms in the regolith to form water. Okay, so the regions where we find all the water on the moon are in these regions called permanently shattered regions. So these are regions near the moon's poles, the north and south pole, that never experience direct sunlight, and this is a consequence of the fact that the moon, the spin axis of the moon is perpendicular to the ecliptic plane. And so as it orbits the Earth, some of the polar regions never experience direct sunlight. So on the left is an image from the Lunar Reconnaissance Orbiter, which is a spacecraft that's currently in orbit around the moon. This is a view of the South Pole, and you can see there are these craters at the South Pole that are shadowed, and these are usually within at the crater floor where the neighboring topography is shielding the floor from the sunlight. The plot on the right here is the South Pole again. This is a map, so you're looking directly at the South Pole. So the South Pole is right here, and then you move towards the equator as you go up. So this is from a paper by Mazarico, and what this is showing is that all of these red areas are permanently shadowed, so they never receive any direct sunlight. And because they never receive any direct sunlight, the temperatures in these regions are extremely cold and can reach as low as 273 degrees Celsius. And so in the early 90s and 2000s, there was a lot of data that suggested that there was ice in these permanently shadowed regions at the moon. And so we really wanted to detect it directly. So what we had a signature of hydrogen, which is, of course is part of water, but we wanted to directly detect the water that was there. And so we devised this experiment called the L-Cross experiment. So when the Lunar Reconnaissance Orbiter was launched to the moon in 2009, it included this companion mission called the L-Cross experiment. And the idea with this is a little bit wacky, which is good sometimes. But what happened was that you had this, the upper stage of the rocket, which was used to launch the spacecraft to the moon. And so they launched the upper stage of the rocket into one of the polar craters, which was suspected to have ice. And the idea was that the rocket would crash, and then immediately following the rocket would be the spacecraft, the L-Cross spacecraft, which is equipped with various instrumentation. And so it had about a 5 to 6 minute time delay. And so the spacecraft crashed, it created this plume of material, and the spacecraft analyzed the plume and then sent all of the data back to Earth, and then it itself would also crash into the Earth, or into the moon. And so what this experiment showed was that indeed there was water present in the polar craters, and the plume was about 5% ice, which may not sound like a lot, but the abundance of ice that we've detected in the moon is actually quite significant. So with the presence of the moon, the next logical question is, why is it important? Well, there are really two answers. One is there's a scientific answer. So the accumulation of ice in these concentrated areas at the moon kind of tells us about the history of the delivery of water to the inner regions of the solar system, including the Earth. And the moon is a relatively pristine environment. There's not a lot of things that might kind of disrupt the evidence of water there. So a second reason is exploration. So there's kind of been this idea floating around that we might one day colonize the moon. This was kind of more popular in the 60s. It was sort of seen as a natural conclusion to the space race. In the early, late 50s, the U.S. Army was developing plans to establish a military outpost on the moon, which is kind of terrifying, and it's a bit of a sign of the times. But there are still practical reasons why this might be a good idea, and there's certainly a debate to be had about the merits of it. But there are resources on the moon that we might be able to extract. The moon, again, has a lower surface gravity, so it might be cheaper to launch rockets, assuming we had a way to get fuel. There are ideas about putting an observatory up there. And so if there is ice present on the moon, and we know that there is, that might be instrumental in developing this human colony. So moving on to Mars, the red planet, the crowd favorite. Mars really is an interesting and dynamic world. A little bit of background information. Being further from the sun than the Earth, Mars receives about half the total solar energy. So the surface temperature is quite a bit lower. The average surface temperature is about negative 60 degrees, although this does vary significantly depending on where you are on the planet. It does have an atmosphere, but it's extremely thin. It's about 150 times less pressure at the surface of Mars than there is on the Earth. We do find evidence of water, but because the atmosphere is so thin, water can't exist as a liquid. So if you were to place a glass of water on the surface of Mars, it would immediately begin to boil and freeze almost at the same time. But the question we're all asking ourselves is, was Mars wet in the past? Did it have water in the past? Was it habitable in the past? So we want to answer this question of could liquid water have existed on Mars? Is this what Mars could have looked like 3 billion years ago? Well, maybe. This is probably the best case scenario. I have to admit that as a scientist. This is Mars with a huge global ocean and water cycle. And so this is kind of the most extreme example, but it could be something a little bit less extreme. But we just don't know. So because Mars is such an interesting place, it's gotten a lot of attention. Here's just kind of the family portrait. This is showing all of the various missions that have flown to Mars over the years, from all the different countries, from the US and Europe and Japan, and Russia has also tried really hard. And so collectively, these missions have revealed an incredibly interesting and dynamic world, both past and present. And there really has been an abundance of evidence for the presence of water on Mars. And I'll show a few examples of that here. This lower left-hand image is an example, an image that was taken by the Opportunity rover, which is still operating on the surface. So one day it was roving around Mars and it came across these interesting mineral deposits, which we named blueberries because they kind of resemble blueberries, although these are actually gray, not blue, and they're also the size of a BB, so they're a little bit smaller, but I don't want to be too pedantic here. They are iron-rich, and from what we know about how these minerals form, they need liquid water. So they need standing liquid water, and these minerals condense out. And so this was really one of the first pieces of evidence that water existed. So another line of evidence is that we see these flood channels on Mars. This is this middle picture. This was taken by the Mars Express spacecraft. You can see all of these grooves that are carved into the surface. And these form when water kind of rushes in. So this is a flood. This is a kind of a one-time event. And we see these all over the planet. This is another example. This is from the Mars Global Surveyor. So this is a river delta, and we see these on Earth in quite a few different places. And so this was one of the first evidences of persistent liquid water on Mars in the past. So these occur when you have a river that flows into a larger body of water, and it deposits all of these sediments, and it makes this kind of fan shape. And this is very characteristic of what a river delta is. So we have all of this evidence for a watery, wet Mars in the past. But there's an interesting paradox in planetary science, which is known as the faint young sun paradox. This was proposed by Carl Sagan and George Mullen in 1972. And it's this idea that stars go through a life cycle. So when they're born, they don't have as much energy, and they kind of develop more energy as they go on, and it might be a little curved. But when they're born, they have about 70% less energy. And so we have all of this evidence that shows that Mars was once wet and warm, but the sun wasn't putting out as much energy at that time. And so it doesn't really make sense that Mars had all of this water. And so we really haven't been able to solve this. The climate models don't predict a warm and wet Mars with the temperatures that it was probably experiencing at the time. So there's a lot of evidence for water on the surface of Mars today as well. One of the largest deposits that we see of ice on Mars is at the North Pole. So here's an image of the North Pole. And most of this is composed of water ice, although there is some carbon dioxide ice as well in there. And when you look at Mars through a telescope on Earth, you can see the North Polar Cap because the ice is so bright and reflective. And so we've known about ice on Mars for quite some time now. What's a relatively new discovery is that there's a lot of water in the subsurface of Mars as well. So this image is from the Mars Odyssey. It's a neutron data, so it scanned the planet. And what it found is that there's a lot of water beneath the surface. So these red areas correspond to lots of water. These blue areas correspond to a little bit of water. And it's not just the poles, it's all over the planet. So this map shows is a global map of Mars. It's the same data, just showing the entire planet now between minus 60 and plus 60. So again, the red areas are high water concentration. Blue areas are a little bit of concentration, 2%. So most of it's concentrated at the poles, but we do see it all around the planet as well. We've even actually imaged it. So this is an image in the upper left taken by the Phoenix rover, which landed in a northerly region of Mars. And it had a little scoop, and it dug just a few inches below the surface. And we imaged this ice, and then a few days later we imaged it again, and it was gone. So water is stable below the surface, but when you expose it to the conditions above the surface, it will begin to sublimate. So in addition to ice being on the surface of Mars, we also find it in the atmosphere in the form of clouds. And this is a bit of an expertise of mine. I spent 2 years during my master's degree studying Martian clouds, but I won't bore you with the gory details. But clouds do play an important role in the Martian climate today, as they do on Earth. And they do so in a couple of ways. One is through the regulation of temperature. So because clouds will transmit visible radiation, but they will absorb infrared radiation from the surface, and so this has kind of a greenhouse effect. So it warms the planet. And they also act as a conduit, so they transfer water from one region of the planet to another. Okay, so here are a few more images of clouds. On the lower left here, we have clouds taken from the Opportunity rover in 2006. You see these very thin, wispy clouds in the atmosphere. And these are akin to cirrus clouds on Earth. These are the high altitude, very thin, composed of water ice. Mars does also have carbon dioxide clouds, but I'm just going to kind of focus on water ice clouds as well. And here's an image of a global image, which is taken by the MARSI camera on the Mars Reconnaissance Orbiter, so taken from orbit of Mars. And we also see these kind of thicker clouds, and these are clouds that are formed due to the topography that's there. So this image right here, or this area right here, is Olympus Mons. This is the largest volcano in the solar system. It's taller than Mount Everest. And what you have here is just you have air being forced upwards, and as it rises, it cools, and all the water condenses out. And this region over here is the Prince volcano. So there are three more volcanoes here. So we see these types of clouds on Earth as well. So for my final slide of Mars, I wanted to talk about the Phoenix mission just a bit. So the Phoenix mission landed on Mars in 2008, and it landed in a northerly region of Mars. So here's the North Pole, and this is where the Phoenix lander landed. And one of the instruments that it carried is a LiDAR instrument, which is kind of conceptually simple. It just consists of a laser and a detector. So what they did was they pulsed the laser directly into the atmosphere, and then the signal would be scattered off of particles in the atmosphere, such as cloud particles and dust particles. And it would be reflected back toward the spacecraft, where it'd be picked up by the detector. And one of the days when they made this measurement, this is what they observed. This is kind of what the LiDAR sees. So time is on the x-axis, and altitude is on the y-axis. So this red portion here is water ice clouds. These are fairly low altitude. But in this region here, you can see these kind of tails that form from the clouds. And what this is actually showing is active snowfall on the surface of Mars. So this is the first time that had ever been detected. And I thought that was pretty cool. Okay, so we're kind of moving on into the outer solar system, and to make a quick pit stop at the Asteroid Belt. So most people know that the Asteroid Belt is located between the orbits of Mars and Jupiter. And I'm not going to spend a ton of time talking about it just because I want to kind of discuss a few other things, but the Asteroid Belt really has played an important role in the solar system through the delivery of water to the inner regions of the solar system in particular. So for the most part, the orbits of these asteroids are happy now, but occasionally their orbits will be disrupted from gravitational influence, and their orbits get disrupted, and they get sometimes forced to the inner solar system, and we see kind of collisions and with Earth, and so that's most likely the reason, or the way in which Earth and bodies like Earth and Mars and the Moon came to have its water. So we hope to never see this again, although during the early part of the solar system, this was quite common. Okay, so moving on now to the Galilean satellites. These are the 4 largest moons of Jupiter. I think Jupiter has over 60 moons, but the 4 largest are referred to as the Galilean satellites, or the Galilean moons, named after their discoverer, Galileo Galilei, who discovered them in 1610 using the newfound invention of the telescope. And here's a view similar to what Galileo would have seen. Kind of in order of closeness, you have Io, Europa, Ganymede, and Callisto. So here's what they look like up close. Each of these worlds is incredibly interesting in their own right. Io is the most volcanically active body in the solar system. It has over 400 active volcanoes on its surface today. Europa, I'll speak about next. And Ganymede and Callisto are both incredibly interesting worlds, and I will kind of touch them. I won't speak about them a lot, though. So here's the kind of a larger image of Europa. Europa is an icy world. Most of what we know about Europa comes from the Galileo spacecraft, which orbited Jupiter for 8 years and made 12 flybys of Europa. And so Europa is about the same size as our moon. It's about 3,100 kilometers in diameter, but it definitely doesn't look like our moon. It looks very different. You have these bright plains that are crisscrossed, kind of crisscrossed by this darker material, and these are regions of higher mineral content. So it's still ice, but it's just a regions where there's a little bit more minerals. One thing you'll notice, though, is that there are very few impact craters, and what that tells us is that it has a very young surface. So Europa formed with the rest of the solar system, so it's 4.5 billion years old, but the surface is only 600 million or 60 million years old, give or take. And so what that tells us is that there's some way that the surface is being renewed, because we know that there are impact craters that have pelted this body, as with all other bodies in the solar system, but we don't see any today. There are only really a couple. So the most intriguing thing about Europa is that it has a global ocean beneath its surface, and I'll talk about that next. So here's what the interior of Europa might look like, an animation of that. So if we're able to kind of take a chunk out of Europa and view the insides, this is what we might see. You have a metallic core and a rocky interior. So actually most of the planet, or most of the moon, is made of rock. But the outermost region, kind of a thin veneer, is made out of ice and water. So kind of zooming into what the crust of the body looks like, you might see something that looks like this on the right. So you have an icy shell, and we don't know exactly how thick that is. It could be, estimates kind of vary between 60 and 100 kilometers. There is some people who think it's a lot thinner, but we don't exactly know how thick it is. But beneath it you have an ocean of salt water, and the depth could be as much as 150 kilometers below the surface. And so this is a substantial amount of water that exists in this body. So if you were to extract all of the water on Europa, and you compare that to all of the water that's on the Earth, what you would find is that Europa might actually have 2 to 3 times more water than the Earth does. And it's really quite spectacular. Again, given what we know about life and its kind of requirement of water. So Europa might be one of the best places to go searching for life. So how do we know that Europa has a subsurface ocean? I mean, after all, we can't see it. We haven't yet detected it directly. Well, there are a couple lines of evidence. One is geological. So we look at Europa's surface and we see that there are certain features that that are best explained by the presence of a subsurface ocean beneath subsurface ocean. But actually the most convincing data comes from magnetic data. So the Galileo probe, which orbited Jupiter, had a magnetometer. And first I should say, Jupiter has a very intense magnetic field. So it actually stretches all the way to Saturn. This is kind of an artist's conception of what that might look like. But all of the moons of Europa are orbiting within this magnetic field. And so the Galileo probe had a magnetometer. And on one of the flybys of Europa, it detected that Europa also had a magnetic field. And the way in which so what that tells us is that there's something below the surface that is conducting electricity. And that is actually best explained by an ocean of salt water. So how does Europa come to have a subsurface ocean? I mean, after all, it's way outside of the habitable zone. So it's supposedly far too cold for liquid water to exist. Well, there's another source of heating called tidal heating, and this operates as Europa orbits Jupiter. So its orbit is not a perfect circle. Sometimes it's a little bit closer to Jupiter, sometimes it's a little bit further. And when it's closer, it's being stretched, and when it's further, it's being compressed. And this stretching and compressing produces heat. It's a kind of frictional heat. So Europa orbits Jupiter about every 85 hours, every 3.5 days. And so over that period, it's constantly being stretched and compressed. And the best estimates are about 30 meters. So for comparison, Io, which again is the most active, volcanically active body, stretches about 100 meters. So that's because it's orbiting a little bit closer and it has more tidal heating to give it that level of activity. So there are a couple of missions that are planned to go visit Europa because it does seem like such an interesting world. One of those is JUICE. JUICE stands for the Jupiter Icy Moons Explorer. It's being developed by the European Space Agency. It's going to study Ganymede and Callisto and Europa. It's going to launch in 2022. And one of the main science objectives is to determine whether or not there are organic chemicals on the surface. That's one thing that we don't yet know that we really want to know because in addition to water, organic chemicals are also an ingredient for life as we know it. So the other mission that's being planned, although this one is not as advanced in its kind of progress, it's in the design phase. It's called the Europa Clipper. So it will orbit Jupiter, but it's going to kind of focus specifically on Europa. It's going to make 45 flybys, and in that time it's going to make all kinds of measurements. Not sure exactly when it's going to launch yet. But one of the most exciting instruments that it'll carry is an ice-penetrating radar. And so it'll actually be able to see how thick Europa's ice shell is. And that will be really crucial because if we can actually explore the oceans of Europa, first thing we'll need to do is determine how thick they are. And if they're 100 kilometers thick, that's going to pose some serious challenges. Whereas if it's only a couple of kilometers thick or a few tens of kilometers thick, that's a little bit more reasonable. So now we come to the other two Galilean moons, which I haven't talked about. So there's Ganymede and Callisto. And both of these worlds are extremely interesting, and I'm not going to kind of give them the attention that they deserve in the interest of time. But both of these moons also have subsurface oceans, again through this process of tidal heating as it's being stretched and compressed. Ganymede is the largest moon in the solar system. It's actually bigger than the planet Mercury. It has tectonic activity on its surface. So if its surface may be rotating kind of beneath the ocean, so the icy ocean. So that might be what gives rise to the tectonics that we see on the surface. Callisto is also quite large in size. It's the third largest moon in the solar system. I think it's about the size of Mercury. From the outside, it seems a little bit less interesting. It's a heavily cratered, which means there's not a lot of activity at the surface, but the models predict that there's also a global subsurface ocean beneath the crust. So moving outwards, once again, we come to Saturn and one of its moons, Enceladus, one of my favorite places in the solar system. It was discovered by William Herschel in 1789, and like Europa and most bodies in the outer solar system, it has an icy shell. There are regions which are cratered. As you can see here, all of these craters, it's a relatively dense area. But there's this region, you can almost draw a line here, where all of this side of the planet is relatively free of craters. There's virtually free of craters. There are none. And so what this is telling us is that there's some resurfacing event that's happening. So there's something that is erasing these craters. And like Europa, Enceladus also has a subsurface ocean. This one we've been able to actually more directly detect. And it just comes from this process of tidal heating as it's being stretched and compressed. Okay, so a little more background information. The upper left here is a size comparison of showing the Earth and the Moon, and up here is Enceladus. So Enceladus is really, really small. It's only about 500 kilometers in diameter. The orbital period is about 33 hours, so it's whipping around Saturn pretty quickly, which is the reason it has so much energy. So for smaller bodies, we don't really expect them to be very active. The smaller the body is, the more quickly it's losing heat. And so we expect these smaller bodies to be colder and more geologically dead. But with Enceladus, that's not the case. So the first kind of indication that something was unusual with Enceladus came from when Saturn's E-ring was detected. So here's an image of Saturn. This was taken by the Cassini spacecraft, which was in orbit around Saturn. I don't know how long, but just recently, I think last year in September, it crashed into the planet intentionally. 12 years. And so here's one of the images that it took, and this is really one of the most beautiful images that's ever been taken by a spacecraft. So this is Saturn eclipsing the sun. So the sun is behind Saturn, Cassini is out front. And one of the things that you can notice is this E-ring, this very tenuous kind of halo around Saturn. And so it was immediately noticed upon the detection of the E-ring in 1966 that Enceladus is orbiting kind of smack dab in the middle of this E-ring. So the immediate hypothesis was that Enceladus must in some way be contributing to the E-ring of Saturn. So here's another image from the Cassini spacecraft. Enceladus is right here, right in front of this kind of white dot. Here's Saturn's E-ring, and you can see Enceladus is orbiting smack dab in the middle, in the densest part of the region. And because of its position in Saturn's E-ring, we wanted to know kind of what was going on. So there was motivation to image Enceladus, and so that's what we did. So here's an image, again from Cassini, and this is being backlit by the sun, so the sun is behind Enceladus. And you can see this faint brightness here. This is material that's actually being spewed out of Enceladus. It's easier to see when we kind of enhance the image in false color. So you can see this jet that's being erupting from below the surface of Enceladus is actually quite massive. It's ejecting material 50 kilometers above the surface, which is quite a bit higher than Old Faithful in Yellowstone. So here is another image. This was taken on a separate flyby of Enceladus. You could see all of these separate geysers that are erupting. And from what we know about Enceladus is that these are very common. There have been more than 100 that have been detected so far. And so not all of this material is being lost, is contributing to the E-ring. Some of it will eventually fall back onto the surface. And when it falls back to the surface, that is what is responsible for renewing it. That's what's responsible for erasing the craters that we don't see in the southern hemisphere. So the big question is kind of what is inside Enceladus. So once we saw these geysers erupting, there was kind of an obvious desire to fly Cassini through these plumes as they're being erupted. And so that's kind of what we did. The Cassini spacecraft has a mass spectrometer, which is an instrument that allows you to determine what the composition of a material is. And so as it flew through these plumes, it was using its instrument to determine what is inside, because these plumes are being erupted, so this is kind of direct access to the inside of the planet without having to actually go inside of the planet. So excitingly, what they found was that the plume is contained of water, of course. It's actually ice because it immediately freezes once it is exposed to the vacuum, but it detected that there's ice, and it also detected organic compounds. So these are molecules that contain hydrogen or contain carbon and that are essential for all life. So many people say that Enceladus, and I might agree that Enceladus is the most likely place to harbor life, although we still have a lot of learning to do with respect to what is inside, what these oceans could actually look like. So a few other ocean worlds in our solar system that I won't go through in detail, but I wanted to kind of give a shout out to. These are not to scale, but on the lower left we have Mimas, which is a moon of Saturn, aka the Death Star moon. Also has a subsurface ocean. Titan, one of the most interesting places in the solar system, also is believed to have a subsurface ocean of liquid water. In addition to kind of an interesting surface, it has an atmosphere that's, I think, 1.5 times that of Earth's. And it has lakes of liquid methane and rivers of liquid methane. And just an incredibly interesting place that we desperately need to explore. Pluto and Triton, even in the most outer reaches of our solar system, we find evidence for subsurface oceans. So these are kind of vast expanses in our solar system that contain liquid water that we really know nothing about at this point. So to kind of wrap everything up in terms of the outer solar system worlds, this was an image that was done by NASA and JPL Caltech, and it just kind of shows a size comparison of all of the ocean worlds of our solar system. So you can see Earth is by far the largest, but it doesn't have the most water. Enceladus over here is the smallest, although in this case size doesn't matter. Europa, Pluto, and Ganymede way out front. So a lot of the solar system is very watery indeed, which is a kind of an exciting prospect. So to date there have been about 3,700 exoplanets that have been detected. These are worlds beyond our solar system. And although we can't image them yet directly, at least we can actually see what's on the surface, the science that we're able to do at this point is becoming increasingly sophisticated. And so there have been a lot of detections of water in the atmospheres of exoplanets, but that's really all we've been able to do. But we know that the universe is full of these worlds, and it's really exciting to be kind of at this stage in exploration of not quite knowing, but kind of being just really led and kind of have clues about what actually could be in these worlds. So to conclude, we really do live in a watery solar system. Water in all its forms is abundant. And what does this say about life? Well, we don't know. It's only through exploring these worlds that we'll actually be able to find out. And if we do happen to detect life on another world in our solar system, well, just by extrapolation, that says a lot about the abundance of life in our universe. And if it goes in the opposite direction, well, that says something about how rare life is. And so it's only through exploring these worlds that we can actually sort of get a handle on on how common life is in our universe. And if nothing else, I hope what I've done tonight is to show you that these worlds are definitely worth exploring. So with that, I will conclude, and thank you for your time, and we'll take any questions if there are any.
Ah, very good. I was going to say we're going to need some lights here. So before I hand, well, you've got your own microphone. I'm not going to hand you a microphone. But before I hand you the floor, interesting, your life is actually going to get a lot busier starting next week. TESS is launching the Transiting Exoplanetary Satellite.
Yeah.
So that 3700 is probably going to go close to doubling over the next 5 years. So more real estate for you to work with.
Yeah,
okay, more water to find. Okay, so I am going to hand the microphone to this fine gentleman here who will run it around the audience along with Sean. So when you have a question, Jake, I'll let you field them, but please speak it into the microphone so Andrew doesn't get upset with me about capturing it.
You said that Pluto had a subsurface ocean. Is it liquid? Or and if it is, how did it get heated up?
Yeah, that's a good question. I don't know much about the Pluto system, unfortunately. As far as I know, I think it is liquid, but I don't know what the source of heating would be, because it wouldn't come through tidal heating. So it is a good question, but I don't know.
What got you interested in this particular area of the astronomy?
I guess I kind of fell into it. So for my master's degree, I was studying water ice clouds on Mars. And we were looking at, I was a part of the Mars Science Laboratory rover, the science team. And so I guess for my PhD work, I've kind of moved on to studying ice on the moon. And so the common theme between those two projects has been the presence of water. I think it's just a really interesting area of science right now, from what we're able to kind of, what we've uncovered so far with the presence of water and just how abundant it is. And also, you know, the implications for life, I think, is a really interesting thing as well. The fact that we know so little about how life formed and what the requirements are. So we have this kind of this one test case on Earth, and I think it'll be interesting to see kind of what the exploration tells us.
What kind of biological life do they think they might find in these water worlds or water in the solar system?
Oh, I don't know. I think that's anybody's guess. I think approaching the question kind of in this way, there's a little bit of anthropocentrism that kind of creeps in, where it's our understanding of life is biased toward what we know, what we consider life. But I think the sky's the limit when it comes to life. I mean, there are common denominators. There are certain ingredients that we feel, certain common denominators in life on Earth. But you know, silicon-based life could be a potential as well. Although carbon certainly seems like a good choice for life to form, given its kind of variety.
Where would the source for the water on Earth be? My understanding is like the moon was formed through a collision. So wouldn't everything been boiled off at that time?
I think the collision was before the Earth got its water, if I'm not mistaken. So if that's the case, then the water delivery would have been after that collision. Or, yeah. Yeah. So the water, most of the water that's come from Earth, I think, has been through the delivery from comets and asteroids.
The source of liquid water, more than anything, I guess, is mostly the likely source of life. As you go further away from the planet, say Jupiter, are the more distant moons have less abundant liquid water than the ones that are closer in and therefore affected by gravity?
No, I don't think the distance from the sun is actually going to be the. Oh, yeah. Yeah. No, I don't think so. I think Ganymede actually has the most liquid water. So that's the prediction. So Europa is closer, but Ganymede's further. So Ganymede is a bigger body. So I think just there's more potential there. So there are other things that are considered.
Hello.
Hey.
We seem to be living in a very fortuitous set of circumstances. Earth has a magnetic field. It has a core. It has a powerful enough gravitational field that it can hold on to its atmosphere. All right. Do I start again?
I heard what you said.
All that, and I have to start again. Well, in 2 words, Earth has a magnetic field. Mm-hmm. It has a metallic core, and it has a gravitational force that holds its atmosphere together in a relatively good way. Whatever happened to Mars, do you think? Because if it did have an atmosphere, it still has a trace. My understanding from what I've read is it doesn't have any magnetic core anymore.
Yeah.
And it has no magnetic field. So
I think
has your work taken you there?
No, it hasn't, but I think I kind of know what you're getting at, and I think it is because of the loss of the magnetic field. So the solar wind has been kind of chipping away at the atmosphere, and so because of the energetic particles that are coming from the sun, Mars doesn't have a very strong gravity, and so the lighter molecules will be kind of stripped away and as they're energized. And so the MAVEN mission, which went into orbit around Mars a couple of years ago, has been actually seeking to explain that exact fact. Why did Mars lose its atmosphere? Mm-hmm.
He asked my first question, but I had a follow-up question. Obviously, there's a mechanism in Mars to get rid of the water rather, over geological time. I've heard talk about terraforming Mars, where you add gases or you do something to end up warming it, and then the water becomes liquid. To me, given that Mars has lost a huge amount of water already, that probably wouldn't last very long. Have you heard of any studies on that?
No, that's not something I've looked into a whole lot. I do think there's kind of a lot of challenges involved with that, and I think that's kind of a long way off. As you said, there's subsurface water, and so we can kind of heat the atmosphere by kind of releasing that into the atmosphere if we could find a way to do that. So that would have a warming effect, but the atmosphere still isn't going to be strong enough to maintain it, and so we would also have to build up the atmosphere in some other way. So most of Earth's atmosphere is nitrogen, so we need some sort of inert gas that's going to pressurize the atmosphere, and I'm not sure if there's a way to do that, or I'm unaware of a way to do that. So lots of challenges involved with that.
That image that showed the laser shooting up into the clouds on Mars, and there was like a snow streak, if you will.
Yeah.
Will that actually reach the ground, or would that sublimate before it gets there?
I think it does actually reach the ground, although it won't stay on the ground for very long. But the clouds are low altitude. They're part of the planetary boundary layer, so it's the kind of the lowest region of the atmosphere. And so given that the snow doesn't have that far to fall, I think it does actually reach the ground, but it just doesn't stick for very long.
Might have exhausted the questions. Jake will be around afterwards, so if you think of anything more, by all means, and rumor has it that he'll be with us at the meeting after the meeting as well, so you'll have ample opportunities. So let us thank him one more time, please. Thank you very much indeed. one calendar. We actually have two items, but I have only got one in my hands at the moment. But 2018 RASC calendar.
Excellent.
You know, it's only 3 months old, so it's sweet. Enjoy.
Thanks.
Thank you once again. Okay. And I'm going to ask Andrew where he wants me to stand. About here? Yeah, good. Okay, right. So, a little bit of the business part of the evening, folks, just to keep you up to date on what is happening in the realm of the RASC Toronto Centre. Our next meeting, as I indicated at the beginning of tonight, we have two types of meetings, speakers' evenings, and then in between, 2 weeks from now, in this case on April 25, is our recreational astronomy night. There will be three of our members who will be holding forth on the various topics that you can see there. Same location, same starting time, although there is a little bit of hangout time before the meeting, so if you're here from 7 till 7:30, feel free to just chill, but the meeting will be starting promptly in and around 7:30. So that's on April 25th. Our next meeting, our next speakers night into the month of May 9 in particular, as I also warned you, a York doubleheader. And this one is one of our graduating master's students. And I'm just going to say Janikin because doing his surname, I've been practicing for 2 years, no good at it yet. So Janikin is a graduate student associated with Professor Michael de Robertis, who has spoken to us here as well. And Janikin will be giving us the latest scoop on galaxies, if you will, and what's happening at the centers of galaxies. Yes, very big. And no longer alone, it appears. Anyway, he'll tell you more about that afterwards. Solar observing. We have International Astronomy Week coming up, and I guess it's the week of Monday, April 16. As Sean has indicated to me, there has been a tradition where literally every day of the week we host solar observing during International Astronomy Week. I didn't know that. At any rate, needless to say, if we're going to be doing that, help. So if anybody is available for that week, any of the mornings, Sean is down here in the corner. By all means, corner him or certainly give him your contact information. But the Ontario Science Centre and the RASC have a long and strong tradition in this regard. And so if you have a little bit of time that particular week, it would be appreciated here in the mornings out there on the telescope. We've got, of course, various star party activities. We have two types of star party activity. One which is sort of dark sky, where we go and see, really nice, interesting objects from a darker location, and then our city star parties, where, of course, we're more engaged with the public and it's in a brighter environment. So, as you can see, the dates here for the dark sky party starting first clear night. So that's the normal way we proceed. We start out on the Monday. If it's nice and clear and we get a go, we do it on the Monday night. If it's not clear, the no-go is given, and we move to the Tuesday, and we work our way through the week, hopefully snagging a clear night Monday through Thursday. And in this particular instance, that is the 16th, starting Monday the 16th of April for the dark sky gathering. And Long Sault, that's still correct, right? The Long Sault Conservation. Yes? Okay, we're going to go with that. Okay, thank you. And then, of course, the City Star Party is the following week, and that is exactly the same arrangement. Remember, we have our Recreational Astronomy Night on Wednesday the 25th, so that won't be included in this run. But we are down at Bayview Village. First clear night, go, no-go, starting on that Monday evening. We also have one other, well, we actually have two other events. You can't see them both yet. One is out at Pickering, the Millennium Square, and this is on Saturday the 20th. Is that start time implying that we do a bit of solar observing before sunset? Yes? Right? Okay, fair enough. I just wanted to make sure it wasn't a typo that had snuck in. So a bit of solar observing before sunset. Daylight saving time has struck, so we've got, of course, a little opportunity there, followed by some nice evening observing and the go, no-go call as always. Yes? Right, so there was a typo, but I didn't pick up which part. I got snookered on the 6th. All right, so it's on the Friday evening. That's the call, Friday evening. Right, okay. Right, so sorry about that. So Friday, April 20th, Millennium Square out there in Pickering. There is also one other event that's taking place that week, obviously all associated with International Astronomy Week. This one is here in Thornhill. It is put on by one of the local councillors there, has been running for a number of years. Jim Laframboise from York University has been one of the prime supporters of this event, but this year, along with York, the RASC is invited for the occasion. Generally speaking, a fun event, and that is the contact information there. That one doesn't have a go or no-go. It's going to happen regardless. Whether or not we can see anything depends purely upon the cloud cover for the evening. We have all sorts of social media action out of the center, and as you can well imagine, it's very important that we keep the messages flowing out from the center to the public as well as to our membership. If you are interested in a little bit of social media tinkering, by all means, we have 3 contact addresses there, and yeah, I'm not even going to guess. Do we actually know the real live identities of those 3, or do we keep it secret? So Tom is one of them, I'm guessing. Okay. All right. So Katrina and. Okay. So by all means, feel free to contact any of those folks there, and if you're interested, that would be fabulous. Many hands make light work, so to speak. The open house. This has been 2 years in the making. June 9 is the return of the RASC Toronto Centre to the David Dunlop Observatory. For those who remember, it was almost 2 years ago in July of 2016 that things changed rather dramatically and very quickly. We are back at the David Dunlop Observatory as of June 9th. Although it feels like we've been hard at work for a much longer period than that. The current DDO committee has been working very hard under Ian and Baravi to get our presence back there on track. Town of Richmond Hill has been working at governmental speed, and that's why it's June 9, because of course they asked us to sort of lay out our plans the better part of 9 months ago. At any rate, we are returning. If you are available to come out and enjoy the festivities, either work or play, by all means please touch base with us. We will need many hands on that day because it will be a public gala event. So there will be observing, there will be tours, and so on. So that's a very good question. We'll go with that. TBA. Seeing I didn't make the slides, I can't actually give you any more insight. Yeah. It wouldn't actually surprise me if the town hasn't quite finalized that. However, I would bet that it wouldn't be before about 11 o'clock. So yeah, we'll certainly get greater clarity as we go forward, but I'm betting it'll be late morning with an official opening probably in the early afternoon. Okay, as I don't see Ian or Baravi in the house, but that doesn't mean that they're not here. No, okay. The Car Observatory season is almost upon us, so by all means, as a part of membership here, you have the opportunity to sign up for access to the Car Observatory, the booking system through rascto.ca. By all means, if this is something that interests you, and it's a great site with great facilities and only getting better, there is the opportunity. I'm not sure whether or not the road is actually open yet. Do we know whether or not the snow has cleared from that area?
It's been washed out in places apparently, so they're waiting for a grader to make it more accessible.
Right, soon is the answer. Yeah, but the Car Observatory, if you're interested in more information, by all means ask us afterwards. The telescope loan program, if you're interested in trying your hand at a new telescope or trying your hand at a telescope for the first time, there are no shortages of telescopes that we have available for you. Do we have our loan facilitators in the... Yes, we do. Okay. So by all means, corner them later on if you're at all interested in borrowing one of the telescopes and trying your... Last but not least, the meeting after the meeting. So when I put down the microphone. This is where many of us will head for a quick drink afterwards, down basically the corner of Mount Pleasant and Eglinton, the Granite Pub Brewery for the meeting after the meeting for your gastronomical enterprises. Are there any other items that haven't been covered that I need to alert people to? Apparently not. So, thank you very much for joining us. Oh, sorry?
The Ontario Science Centre on the 21st.
What about the 21st?
So we'll be having this star party. Listen on the forum.
Oh, okay, in the evening, presumably to culminate in International Astronomy Week. Yes. Okay. Are we being asked to participate, or we're just asked to come along and have fun? Okay, so here...
We'll need volunteers with or without slips.
Right.
So Ian will have more details on
the website.
Yeah, on the website.
Okay, because we're not going to meet much before that, needless to say. Thank you very much indeed. So Saturday, April 21st, for yet another activity associated with international astronomy. We're going to have a very busy week. Let's hope for clear skies all the way along there. Anything else? In that case, thank you very much for joining us tonight, folks. We'll see you next time.